Alright, this lesson here is all about related rates problems, and these are the word problems in calculus that involve rates of change. So everything in these problems are changing as time goes by. So I'm going to introduce this right off the bat, that the main things we're going to need to solve these problems is to introduce rates of change and to differentiate with respect to time, because all of the variables here will change as time goes by. And then the second thing, which is not as obvious, is using the chain rule in these problems. So I want to illustrate first why you need these types of things. So I'll just jot a couple of things down here. So when you describe these situations, when everything is changing as time goes by, you often have different variables that are connected in the problem. So I'll just make something up, say like x to the third power. Okay? Now, if x is a variable that changes with time, then the best way to interpret this is not as x to the third power, but x as a function of time. So this is x of t raised to the third. So as soon as you see something like this, when we think about how it changes with respect to time, x now looks like an inner function. It looks like an inside part of the function, and that's why it reminds us of the chain rule. So now if you were to find the derivative here, so if we differentiate this function with respect to time, okay, so we're looking at it this way, so it would still look as we're accustomed to doing this kind of thing. So it would be 3x raised to the second power, right, the power rule, and then you would look at the inside function and you would differentiate that. So x prime of t. Okay, so now if we just think about how we would normally do this, right, if you were to differentiate x to the third power, you can see the importance of this little piece here, and that's where the chain rule is coming in. So just to summarize what just happened here, when you differentiate x to the third power, we're still going to get what we expect, right, 3x squared, but then we have to multiply by the derivative of the inner function, and this would be x prime, or dx dt, and this is the critical aspect of the chain rule. So we can see it here written out in longhand, where x is a function of t, and this is normally how we would abbreviate that. Okay, so I'm going to take a look at a problem here. We'll see what is happening in this one. And so this is typically what the problems look like in this section. We have a word problem here. We're going to have some given information, some information that we have to find. So this problem here is about pumping air into a balloon. It's a spherical balloon, and it says that the volume is increasing at a certain rate, 100 cubic centimeters per second. So the question in the problem is, how is the radius changing? How fast is the radius of the balloon increasing at the exact moment when the diameter is 50 centimeters? So we might want to draw a picture of the scenario. We might want to write down the information that we have, a little common things that we typically do in math word problems. So we have a spherical balloon, and it is changing. The radius is changing, and the volume is also changing, and we should write down some of the important information here. Okay, so this here says the volume is increasing at the rate of 100 cubic centimeters per second. So this statement involves how the volume is changing with respect to time. So that's a piece of information that we can write down. So this here is dv dt. Tells us how is volume change with respect to time. So we have 100 cubic centimeters per second. So that is given information. And then the question is, how fast is the radius increasing? So they're asking us here in the problem about dr dt. So they're saying, what is dr dt? And at the exact moment when the diameter is 50 centimeters. So we could say here when the diameter is 50 centimeters. So it's really saying we know how the volume is changing. How is the radius changing at this exact moment in time when the diameter happens to be 50 centimeters? Alright, so what we'll do here is to see if we can solve this problem. We naturally need some connection between volume and radius. And the context here is a sphere. So we could look this up if we wanted to, or you might remember it for a sphere. So this is what it looks like. So the volume here is 4/3 pi r cubed for a sphere. And notice this equation is a useful one to use because it does involve the volume and the radius. So an extra step that I'll include here, because this is the important part of related rates, is you could really show what is happening in this problem by writing this step. And it's not necessary to write it, but it tells us that as r changes, v is going to change with it, or vice versa. So volume is a function of time, and so is the radius. So this equation here is the same as this one, but it reveals that time is the independent variable. So once we have all of this written down, we need to introduce rates of change into the problem. So we should differentiate both the left-hand side and the right-hand side with respect to t. Right, so we'll introduce the derivatives here. So the derivative of v, this is going to be dv dt. Okay, and then we'll just go right through here. And then the derivative here, 4/3 pi is a constant, so we'll just carry that into our answer. And then this is where we saw what we saw earlier, that the derivative here will be 3r squared. So we could say 3r squared, and then we have to multiply by the derivative of the inside part. So this will be dr dt. So that is the chain rule that we're using right there. So then what we should try to do is to simplify this equation a little bit, and then see if we can use the given information to solve the problem. So a little bit of cancellation here in the 3's. So it looks like dv dt is equal to 4 pi r squared, and then dr dt. So this equation in red will probably give us what we need, right, to solve the problem. So if you look now at our information, this is given in the problem, how the volume changes. This is what is sought after, the dr dt, and the diameter is 50, so we could use the fact that r is 25 in that case. So we could put all the relevant information in here and then solve for dr dt. Okay, so I'll get rid of the stuff on the top because we no longer need this. Okay, so I'll just highlight, this is the equation that we're using here. So you can plug in all of the relevant information and that should do it. So this is equal to 100. So 100 is equal to 4 pi, and then we have r squared, so r is 25. And then what we're after is dr dt. Okay. So now we just have an equation with one unknown thing, dr dt, so we could simply divide this entire equation both sides by this expression, and we would be done with the problem. So we're going to have 100 here, and then divided by 4 pi 25 squared, and this will be dr dt. So this will describe to us how the radius is changing at that moment, right? So how r changes with respect to time. Okay, so we're all set here. So if you want to simplify a little bit, you might as well do it. You can see 25 times 4 is going to be 100, so there is some simplification here, and you'll have an extra 25 on the bottom. So just for kicks, it's always good to simplify. It doesn't hurt. It looks like this, right? 1 over 25 pi. And this is equal to our rate, so dr dt. So that's the expression that we end up with there. And the units here in this problem, right? This is how the radius changes with respect to time. So this, the units will be centimeters per second. So that's how the radius changes. It would be nice to convert this to a decimal so we can interpret it more carefully. That's always a good idea. So this is a pretty small number, so we can just round it off here. So it's about 0.0127 centimeters per second. So that is the rate that we're after in this problem. That is how the radius changes with respect to time, our information here. So a good habit here, always in these problems, is just to reflect on the answer, make sure that this makes common sense, because sometimes it's not intuitive at all. So if you go back to the problem and what we're talking about, right, the sphere is changing in size, right, the volume. So you can look back at what this problem was really saying. Okay, so it says the volume is increasing at the rate of 100 cubic centimeters per second. And they're saying when the radius is 25, how fast is the radius changing? So we could argue that it seems like the volume is changing pretty quickly by 100 cubic centimeters per second, but that the radius is barely changing at all. So this is like a fraction of a centimeter per second. So if we stop for a minute and think about that, this is something that makes sense. So notice that a very, very small change in the radius of a sphere will result in a fairly large change in volume, because as the radius changes even just a little bit, that is going to change all the way around based on the shape of the sphere, and as a result, a small change here results in a very large change in the volume. So this answer is a pretty reasonable one. Alright, so the last thing to talk about here, and this is related to this problem and almost all related rates problems, is that sometimes you can use a set of guidelines to help you solve these problems. I would say about 85% of the time these guidelines are useful. You do have to be careful because in some problems they are sufficiently different and then these guidelines don't really help. So I'll just go through them quickly. In some of these problems you might want to sketch a picture and assign the appropriate variables. So you can see in this problem, a picture really isn't essential, but you need your R and you need your V. So you need to introduce all of those variables. The second thing is to write down what you have and what you need to get. And in this problem we had the diameter value and then also how the volume was changing. What we didn't have was dr dt, so that's an essential step. The third step is to write down the relationship that is occurring in the problem independent of time. So even though time is ticking, the relationship between the variables stays the same. And in this problem, that was the volume equation. Volume equals 4/3 pi r cubed. So the most critical aspect or critical step of the problem is step 4, and that is to bring rates of change into the problem by differentiating with respect to time. So this is the step 4, where you need to use the chain rule. And then once you isolate what you're looking for, just use the given information and see if you can solve the problem.